Okay. Okay. All right. So we've seen that if I take small enough vectors in the tangent space at a point P, then geodesics with those small initial conditions, they are defined on a fixed interval, say -2 to 2. And so then we can define what's called the exponential map on a subset of the tangent space at P, taking values in M, and basically it sends V, a vector V, to the value of the geodesic with initial conditions PV at time 1. Okay. All right. Okay, so this is a picture. So this domain of the exponential map is vectors so that the corresponding geodesic is defined for time 1. Okay. And so as we've seen, this contains a ball around the origin, right? Okay. So this is a TPM. And what is XP doing? This is a vector V. So the exponential map is mapping into M, my manifold. So this is P, and I'm taking the vector V, and then I'm taking the geodesic with initial conditions P and V, and this gamma of 1 is defined to be XP of V. Okay, where gamma has initial conditions PV. Is this okay?
Yes.
Okay. Okay, so what will XP of TV be if T is a real number? Okay. Then this is going to be what? By definition, this is going to be gamma of T dot theta at 1, right? Where theta is PV and T dot theta is P comma TV, right? Yes?
Yes.
But this, by homogeneity, this is equal to gamma theta of T, right? Okay?
Yes.
By homogeneity of geodesics. Okay. So what do we get? Therefore, we get that gamma theta of T, that means the geodesic with initial conditions PV, this is equal to XP of TV. All right. So that means that XP, the exponential map, it sends straight lines through the origin, right, in the direction of V. So this is, say, TV. Okay. This, the exponential map sends it to geodesics. In M. All right. Is this clear?
Yes.
Okay, so straight lines through the origin only, not through other points. They map to geodesics through P. Okay. So the exponential map sends straight lines through geodesics. Okay, so any questions? Is this okay?
Yes.
Okay. Now, so the exponential map is defined at least on a ball around the origin, right? So some ball, let me call it B0 delta in TPM. To M, okay? And so it's a smooth map by smooth dependence of ODEs on initial conditions, okay? This is a smooth map. So we can look at its derivative at the origin, right? So let's look at dxp at 0, okay? So where does this go from? So this goes from the tangent space at the origin to TPM, right? Okay. Now, TPM is a vector space. So the tangent space at any point of a vector space, this is naturally identified with the vector space itself, right?
Yes.
Okay. And where is it taking values? Well, XP sends the origin to P. So the derivative is going to be a linear map from this TPM going again to TPM, right? Okay.
Yes.
Okay. Now, what does a vector under this derivative of the exponential map? What will a vector V go to? So it goes to dxp at 0 of V. Now, by the chain rule, the derivative of the exponential applied to V, this is the same as ddt at t equal to 0 of xp of any curve in TPM whose derivative at the origin is equal to V. So I can just take a straight line, right? Yes? This is by the chain rule. This is by the chain rule. Okay. But what is this? XP of TV is nothing but the geodesic with initial condition V, right? With initial conditions PV. So its derivative is just V, right? I mean, this is ddt at t equal to 0 of gamma theta of t, right? And that is equal to V itself, right? Yes?
Yes.
So therefore, this means that the derivative of the exponential map at the origin is equal to the identity map, right? From TPM to TPM. Okay. In particular, the derivative is invertible. Okay. And so therefore, by inverse function theorem, XP is a diffeomorphism from a neighborhood of 0 in TPM to a neighborhood of P in M. Is this clear?
Yes, sir.
Okay. All right. So now let's look at what's in the notes. So, okay. So here we have this. The derivative of the exponential map is the identity map of TPM. So XP is a diffeomorphism from small neighborhoods of 0 to small neighborhoods of P. So now we make a definition. A geodesic ball of center P and radius R is the image of a ball in the tangent space around the origin under the exponential map, such that the exponential map restricted to this ball is a diffeomorphism. Okay. So choose a ball around the origin which is small enough such that the exponential map restricted to that ball is a diffeomorphism. Then the image of that ball in M, this is defined to be a geodesic ball of center P and radius R. All right. Is this okay? Yeah.
Yes, sir.
Okay. And a geodesic sphere similarly is defined to be the image of a sphere around the origin. Okay. Such that X is a diffeomorphism in a neighborhood of this sphere. Okay. In a ball containing this sphere. All right. So, so we're taking a ball around the origin here in TPM. Oh, well, we could take a sphere and we could take a ball. Okay. So say this ball is B0R. And this sphere is, say, okay, so this is the ball. And this sphere is S0 little r. Okay. And so the images of these under the exponential map, these will be, so for example, in S2, okay, you could get a picture like this if this is the point P, say. Okay. So this thing here will be geodesic sphere. And this ball here will be a geodesic ball. Is the picture clear?
Yes, sir.
Okay, so the upper hemisphere of the sphere is a geodesic ball. Okay, of radius. What will the radius be? So the pi by 2, right? Yeah.
Radius is 5.
Yeah. So this will be a ball of radius pi by 2. Okay. Fine. Yeah. So, I mean, in this case, latitudes will be geodesic spheres, right? For the sphere, this is a latitude. Latitudes are geodesic spheres. Okay. Is that all right? Yeah.
Yes.
And the straight lines through the origin, these go to longitudes, and these go to geodesics. The geodesics through the North Pole are longitudes, right? These are the geodesics. Okay. Yeah, these are geodesics. Okay. So, so I'm not going to prove these facts, but the facts are the following. If I take a geodesic ball, which is the image of a ball in the tangent space of radius r around the origin, then for any point q in this ball, so q is the image of some vector v of norm less than r under the exponential map. Then if I take the geodesic gamma q of t, this is equal to xp of tv, where t goes from 0 to 1. So this will be a curve joining p to q, right? Yes. It turns out that this curve is the unique piecewise C1 curve in the whole manifold M of shortest length joining P to Q. Okay. So this I won't prove. This uses something called the Gauss lemma. All right. So I won't prove this, but I'm just stating this. So locally, shortest length curves are given by geodesics. Is the statement clear?
Yes, sir.
Okay. So in this picture, this curve from P to Q, this geodesic is the shortest curve in the sphere joining P to Q. Okay. So this geodesic, this is the shortest curve from P to Q. Okay, so in a geodesic ball, every point in the geodesic ball is joined to the center of the geodesic ball P by a geodesic, right? Which is just the image of a straight line through the origin in the tangent space. And that geodesic, it turns out, is the shortest curve in the whole manifold joining P to Q. Okay. All right. So any questions?
No.
This is okay? Yeah.
So it's just a comment that this will show even that the ball goes to a ball infinite
Correct.
of the
So,
same.
correct. That's right. So this ball, this geodesic ball B, which is the image of a ball in the tangent space, B0R, this is also equal to, as Orkojit is saying, the metric ball Q in M, such that the distance PQ is less than R. Okay, because if I take Q, which is XP of V in this ball B, where norm V is less than R, so V belongs to B0R. And then the geodesic joining P to Q is gamma T is XP of TV. T belongs to 0, 1. Okay. Then we know that geodesics have constant speed. So norm gamma prime T, this is constant equal to norm gamma prime 0, which is equal to norm V, right? This geodesic has initial condition V, right? So gamma prime 0 is V. So that means this this geodesic has constant speed equal to norm V. And so because it is the shortest curve, that means the distance from P to Q is equal to the length of gamma, which is the integral from 0 to 1 norm gamma prime T dt. And gamma prime T dt is constant equal to V. So this integral is just norm V, right? Which is less than R. Okay. Right? So that
Yes.
means that B is, so Q belongs to the metric ball BPR. Okay. So the geodesic ball B is contained inside the metric ball BPR. And what's not so clear immediately is that the converse is also true, that if the distance is less than R, then it is contained in this geodesic ball. So the metric ball is also contained in the geodesic ball, and so then they are equal. Okay, so yeah. So let me think about that for a second. I'm not sure. Yeah. Oh, right. Yeah, right. Yeah, that's because, yeah, right.
Because of inclination curves, we have, these are given with geodesics in this small question, so we can just look at the geodesic with that initial direction which reaches from P to Q, and then we can look at that radial line in the attending plane at time 1, that will be Q.
Well, I mean, you have to be a bit careful. See, if suppose you take a point in the metric ball, if it is outside the geodesic ball of radius R, so suppose I take a point, say, I don't know, say Z here, which is out. So if it's outside the geodesic ball, the point is what you can show is that any curve from P which goes outside the geodesic ball has length greater than or equal to R. Okay. And for that, you need the Gauss lemma. So the crucial point is the Gauss lemma. So I'll mention the Gauss lemma later, but essentially, if you take a curve which goes outside the geodesic ball, then you look at the part of it which is in the geodesic ball. So this I can pull back because the exponential map is a diffeomorphism onto the geodesic ball. I can pull it back into the tangent space and I look at the curve in the tangent space, right? Okay.
Yes.
I mean, I can
Right.
pull the part of the curve that is inside, right?
Yes,
Not
yes,
the-
just this part. Yeah, so the length is greater than or equal to the length of this part, right?
Yeah.
So
right.
the length of this part will be at least R. And that you do by using the Gauss lemma. You calculate, so the length will be so if I call this curve, say gamma tilde here, then this curve here is the image x of gamma tilde, and then you compute the length. It's going to be the tangent vector will be the image of gamma tilde prime under the derivative of the exponential, and gamma tilde prime will have a radial component and a normal component. All right. So you break up tangent vectors into vectors which are radial and normal.
Right.
Okay. And the derivative of the exponential map, it preserves lengths in the radial direction, and it maps the normal direction to the normal direction here. So by Pythagoras theorem, the length, the exponential map will increase the length basically.
Right.
Okay, so the length of gamma will be greater than or equal to the length of gamma tilde, and the length of gamma tilde, this is just a curve in Rn, right? The tangent space is identified with Rn. So it's a curve in Rn going from the origin to a sphere of radius r. So it has length at least r. Okay. So that's roughly it. Yeah. So I'm not. But the key point is the Gauss lemma. The key point is the Gauss lemma. Okay. So yeah. So I'll talk about the Gauss lemma later when we talk about Jacobi fields. So let me just. Let me just say this here. So can show conversely using Gauss lemma that BPR is contained inside B, okay, and hence B is equal to BPR. Is this okay?
Yes.
Okay. All right. So geodesic balls are also metric balls of the same radius. Okay. And so then we can look at the distance function, right? So as we saw, the distance between PQ, this is the length of this geodesic gamma q, which was equal to norm V, right? We just computed that here. The distance was the norm of V, right? Now, what is V? V is x inverse of Q, right? So that means the distance function, the distance function from P, okay, if I look at this function, the distance from P to Q, this is norm of xp inverse of Q, right? Yes?
Yes.
Okay. So if I look at this function d sub P as a function on the manifold, d sub P of Q is the distance from P to Q, right? Then d sub P of Q is the norm of xp inverse of Q, and d sub P squared is the norm of x sub P inverse Q whole squared. Okay. Now, because the Euclidean norm on Rn, this is smooth outside the origin, right? So that means that this d sub P of Q, this will be smooth on the geodesic ball minus the point P, right? Because P corresponds to the origin under the inverse of the exponential. Is this clear? And the norm squared, on the other hand, the norm squared in Rn is a smooth function on all of Rn. So therefore, d sub P squared will be C infinity on the whole ball. Is it clear? Okay.
Yes. Yes.
Okay, because the norm is smooth on TPM minus the origin, but the norm squared is smooth on all of TPM. And this X inverse is a diffeomorphism, so it's a smooth map. And so dP will be smooth on the ball minus the point P. dP squared will be smooth on the whole ball. Okay. Okay, so the distance function is smooth outside the point P, and the distance squared is smooth outside, is smooth on the whole ball. Okay. All right. Okay, so yeah, so I've stated this, what we were talking about earlier. The geodesic ball equals the metric ball, and the geodesic sphere equals the metric sphere. Okay, so these rely on the Gauss lemma. Okay, these facts. And here's another fact, that geodesics are locally length minimizing. So again, I'm not going to prove this. So for any geodesic from an interval I into M, for any point T naught in the interval I, there exists a epsilon positive such that for all ST in the interval T naught minus epsilon to T naught plus epsilon, say S is less than T, if I look at the geodesic gamma restricted to ST, then this is the unique shortest curve in M joining the points gamma S and gamma T. Okay, so in particular, the distance between gamma S and gamma T is equal to the length of the curve gamma restricted to the interval ST. And this is equal to just a constant times mod S minus T, where the constant is the norm of gamma prime, right? This is a constant, the speed of gamma basically. Okay. Okay, so you can see that in this picture, geodesics are locally length minimizing. Okay, so for example, if I take, say, a longitude in the two sphere S2, so then it's going to wind around the sphere infinitely often, right? It's going to keep going from North Pole to South Pole and back. Okay. So if I take a point T naught here, okay, so this is gamma T naught, then there is an interval around T naught, T naught minus epsilon to T naught plus epsilon, such that if I take any points ST here in this interval, then the portion of the geodesic from gamma S to gamma T, this portion is the shortest curve in the manifold joining these 2 points. Okay, so locally it is a length minimizing curve. Is the picture clear?
Yes, sir.
Okay, but note that globally it is not length minimizing, right? Because if I look at gamma of 0, that's the same as gamma of 2 pi, right? This curve is 2 pi periodic. And so obviously, I mean, on the interval 0 to 2 pi, it comes back to where you started. So obviously it's not length minimizing on that interval, right?
In particular, for bigger than pi, it would actually, because the other part of.
Exactly. As soon as it becomes bigger than pi, so this is gamma 0, and this is S is gamma pi. So as soon as I take any point, say P equal to gamma of pi plus epsilon, then this is no longer length minimizing, right? Because instead of going this way, I would go backwards. This way would be the shortest curve, right?
Yes.
Okay, so gamma restricted to 0 pi plus epsilon is not length minimizing. For all epsilon positive. Okay, and gamma restricted to 0 r is length minimizing for all r less than or equal to pi. Okay.
Yes.
And of course, for r equal to pi, gamma is not the unique length minimizing curves. All the longitudes are length minimizing from the North Pole to the South Pole, right?
Yes.
So you may not have unique length minimizing curves. Okay. Okay. Fine. So
Because at that is the unit radius, and there the whole sphere is mapped to a point. I guess that is still.
sorry, what are you saying?
I mean, like that is because pi is the injected radius here, and like
Correct.
the sphere is that whole sphere is mapped to a south pole. That is
Is mapped to a point. Yeah, that's right. That's
that is the reason we kept like we don't get
correct. Right. Yeah. So what he's saying is that under the exponential map here, the whole sphere of radius pi I mean the sphere S0 pi, this just maps to a singleton, right? The South Pole. This is equal to xn of S0 pi. Okay, the singleton, the South Pole. Yes. So it collapses. So what you're seeing is basically the sphere is a quotient of this disk where you identify the boundary of the disk to a point, which is the South Pole, right? So this is a quotient map where when you take a disk and you collapse the boundary of the disk to a point, you get the two sphere, right?
Yes.
So that's what's happening. Correct. That's right. Yeah. Okay. Any other questions or comments? Okay, so there's less than a minute. So let's stop this meeting and start another one. Okay.
Also, just give me a minute. I will go to the toilet and come back. I'm just joining.
Okay, yeah, me too. Yeah, me too. I'll also go to the toilet. Okay, fine. So we'll join in a few minutes. Yeah. Okay, fine. Okay. 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 So now let's come to what's called the Hopf-Reno theorem, which is about completeness of Riemannian manifolds. So first of all, a Riemannian manifold is said to be geodesically complete if all geodesics are defined for all time. Okay, so for any point P and any tangent vector V in TPM, there exists a unique geodesic defined for all time such that its initial conditions, gamma 0, gamma prime 0, are equal to P comma V. Okay. So equivalently, all integral curves of the geodesic vector field on the tangent bundle are defined for all time. So that means the vector field G is what we call the complete vector field, right? Integral curves are defined for all time. Okay. So for a complete Riemannian manifold, then the flow of the geodesic vector field is defined on the whole of the tangent bundle for all time. Okay. And so this is a flow on the tangent bundle. This is called the geodesic flow of M. Okay. So what does the geodesic flow do? It let me draw you a picture of the geodesic flow. So M is a complete manifold, is a geodesically complete manifold. Okay. And so the geodesic flow goes from the tangent bundle to the tangent bundle. Okay. So V goes to phi t of V, T and R. And how is it defined? Well, if this is your manifold, then given an initial tangent vector V, there exists a unique geodesic with this initial tangent vector. Then you move along that geodesic for time t, and then you take, so V is say gamma prime 0. Okay. And then you take the tangent vector at time t to this geodesic. So this is phi t of V. This will be gamma prime t. Okay. Is it clear? This is the geodesic flow. Okay. So be careful. It's not a flow on the manifold. It's a flow on the tangent bundle of the manifold. All right. Okay. And notice that if I define the unit tangent bundle, to be the set of unit tangent vectors. So the notation for this is T1M. So this is PV in TM such that norm V is equal to 1. Okay. Then since geodesics have constant speed, right? You see, what does the geodesic flow do? It takes PV. I write this as the initial conditions of a geodesic as gamma 0, gamma prime 0. Okay, gamma geodesic. And this maps to phi t of PV, which is gamma t, gamma prime t. Okay, so norm gamma prime t is equal to norm gamma prime 0, which is equal to 1, say, if PV belongs to T1M, the unit tangent bundle. Okay. So that means the geodesic flow maps the unit tangent bundle to itself. Okay. So unit tangent vectors flow to unit tangent vectors. Okay. And why is it useful to look at the unit tangent bundle? Because if M is compact, for example, then the unit tangent bundle will also be compact, right? See, the tangent bundle is never compact because the fibers are vector spaces which are non-compact. But if I take the unit tangent bundle, then the fibers are spheres which are compact, right? So if the base is compact, M, and the fibers which are spheres are compact, then the total space T1M is compact, right? So, if M is compact, okay, then T1M is compact. Okay. And see, because the geodesic flow preserves the unit tangent bundle, so the geodesic vector field is, I can think of it as a vector field on the unit tangent bundle, right? It's going to be tangent to the unit tangent bundle. At each point of the unit tangent bundle, it is tangent to the unit tangent bundle, right?
Yeah.
Okay. Because after all, I mean, yeah, so, okay. So, so then T1M is compact. So this implies that G is complete, right? Because on any compact manifold, any smooth vector field is complete, right?
Yes.
And once you know that for unit tangent vectors, the geodesics are defined for all time, then by homogeneity of geodesics, you'll get that for any tangent vector, the geodesics are defined for all time, right? Yes, but just by homogeneity, right? If you know that for unit tangent vectors, the geodesics are defined for all time, then any tangent vector is a scalar multiple of a unit tangent vector, right?
Yeah.
So therefore, the geodesic for that tangent vector will also be defined for all time, right?
Yes.
By homogeneity. And so therefore, this means that if M is compact, then M is geodesically complete. Okay. So compact manifolds without boundary, of course, are geodesically complete. All right. Is this okay?
Yes, sir.
So I'm just.
But Hofrino already said.
Yeah, but this is easier to see without
Yes.
Hofrino.
Yes.
Yeah, Hofrino is a more non-trivial statement. I'm saying
right.
the easy
Yeah.
implication which we can see immediately, right? So, sure, yeah. Okay, so right. So as Akrajit is saying, this will also follow from the Hofrino theorem. So, okay. Now, we were talking about geodesic completeness, which means that geodesics are defined for all time, or equivalently, the geodesic vector field on the tangent bundle is complete. But we can also ask whether M as a metric space with the metric induced by the Riemannian metric, whether this metric space is complete. Okay. And the Hofrino theorem states that these two notions of completeness are equivalent. Okay. So, I mean, look, if you take a manifold which is not complete as a metric space, then it should be easy to see, at least in examples, that it cannot be geodesically complete. So for example, if you take M to be R2 minus the origin, right? So this is not complete as a metric space. Right? With the usual Euclidean metric. And this is also not geodesically complete, right? Because if I take any, so geodesics are just straight lines. If I take any straight line which is passing through the origin, then I cannot extend it for all time, right? In this manifold. Okay. Yes?
Yes.
Fine. Just a simple example. So, I mean, so yeah, so the obstruction to geodesic completeness is what the Hofreno theorem is saying, is that the only obstruction is that there are holes in the manifold. Okay, that the manifold is not complete as a metric space. Okay? So the Hofreno theorem will say that if the manifold is complete as a metric space, then it is geodesically complete, and also vice versa. If it is geodesically complete, then it will be complete as a metric space. Okay? So let's give the precise statement of the Hofreno theorem, which is the following. So this is the Hofreno theorem. So let M be a Riemannian manifold and let P be a point in M. Okay? Then the following are equivalent. The exponential map at the point P, this is defined on all of TPM. Okay, so that means equivalently, all geodesics passing through the point P are defined for all time, right? Okay. Right. And this is equivalent to saying that with respect to the distance function on the manifold, closed and bounded sets in M are compact. Okay. So that you can see is false in this example, right? If I take a closed ball of radius large enough so that in R2 it goes through the origin, it contains the origin, right? I mean, this ball will be closed and bounded, but not compact, right? Because it's missing the origin, right? Yes. Right. Okay. And if I take this point, I can see that, you know, the exponential map is defined in all directions except for one direction, right? Which points towards the origin. So the exponential map is not defined on the whole tangent space. Okay.
Right.
Okay, so the third equivalent condition is the metric space MD is complete. And finally, the last equivalent condition is M is geodesically complete. Okay. So notice something interesting here. A implies D. That is, A is saying that geodesics passing through a fixed point P are defined for all time. And D is saying that all geodesics passing through all points are defined for all time, right? So obviously D implies A, that's obvious, but the converse implication is also true. So for completeness, you just need to check that geodesics passing through one point are defined for all time. Okay?
Yes.
All right. And finally, to finish the statement, any of the above equivalent conditions A to D imply that for any 2 points X, Y in M, they can be joined by a geodesic gamma. All right. So any 2 points can be joined by a geodesic. And moreover, we can choose that geodesic to be length minimizing. Okay. So the length of that geodesic is equal to the distance from X to Y. So any 2 points in a complete manifold can be joined by a length minimizing geodesic. All right. So this is a implied by the geodesic completeness or the metric completeness of the manifold. All right. Is this okay? The statement of the Hofrino theorem? Yeah.
Yes, sir.
Okay, so be careful in this last statement. There could be infinitely many geodesics going from X to Y. Right, but maybe only one of them is length minimizing. So of course that you can see in, say, for example, for S2, right? I mean, from the North Pole to the South Pole, there are infinitely many geodesics joining. All of them are length minimizing. But even in, let's say, in a hyperbolic surface, right? What do the geodesics from P to Q look like? So if I take, say, sigma G, say a surface of genus G, which is the hyperbolic plane mod some group gamma, right? So G is, the genus G is at least 2. Okay. So what will all the geodesics look like? They look like the following. So here's my universal cover H, okay, and my quotient is my surface of genus G. Okay. Now, if I take 2 points here, say X and Y, then what will be all the geodesics from X to Y? So there will be the following. Let me take a lift, say X tilde of X, right? Then let me take a lift of Y, all right? So the lifts of, if I take all the lifts of Y, that will be an orbit of the group gamma in H, right?
Yes.
Okay, so let me take the orbit like this. The orbit will look something like this. Okay. Now, because the quotient is compact, what will happen is, see, each orbit point, it lies in a fundamental domain, right? And a fundamental domain will be compact, right? And it will be a compact octagon here, okay? Now, since all the fundamental domains are isometric to each other and compact, so these have a fixed hyperbolic diameter, right? But near the boundary of the disk, the Euclidean metric is much smaller than the hyperbolic metric, right? Yeah,
Right.
because I mean, the hyperbolic metric is the Euclidean metric ds squared divided by 1 minus mod z squared whole squared, or maybe there's a factor 4, I guess. And so the Euclidean metric is equal to a function phi of z into the hyperbolic metric, where phi tends to 0, right? Phi of z tends to 0 as mod z tends to 1, right?
Right.
Yes.
Okay. So that means that if the hyperbolic diameter stays constant, then the Euclidean diameter is going to go to 0, right?
Right.
Okay, and so these fundamental domains, their Euclidean diameter is going to 0, but they tile the whole of the hyperbolic plane. So therefore, this means that the orbit will become dense in the boundary, right? The orbit will become dense in S1. Okay. Right?
Yes.
So
Right.
this is what the orbit will look like. So in the terminology of, hyperbolic geometry, the limit set of this group will be the whole circle S1 at infinity. Okay.
Yes.
Now, what are the geodesics from X to Y going to be? So any geodesic below, it lifts to a geodesic above in the universal cover, and any geodesic in the universal cover joining X tilde to a lift Y tilde of Y, say a geodesic like this, will project to a geodesic below.
Right. Yes.
But then there are going to be infinitely many geodesics from X tilde to all the lifts of Y, right? So all of these are going to project to geodesics below. You see? So these will give you geodesics, which basically they wind around a lot. So maybe this will do something like this. I don't know. And then it comes back to Y. And then you can have much more complicated geodesics, which go around a long way. I don't know, do something like this, come out here, and then go to Y. Okay. So there'll be infinitely many geodesics from X to Y. Okay. And well, one of them will be length minimizing. You see, that will be the geodesic from the point in the orbit of Y tilde, which is closest to X in above. You see?
Yes.
Okay. So the orbit is discrete. There's going to be, a point in the orbit which is closest to X tilde. That geodesic above will project to the length minimizing geodesic below. And interestingly, you see that because the orbit is becoming dense in the boundary, what is going to happen? The set of geodesics from X tilde to points of the orbit, if I look at their tangent vectors at X tilde, then these tangent vectors, these will become dense in the unit tangent circle at X tilde, right?
Yeah.
So that means below, in almost any direction, in a dense set of directions, I can start out in a countable dense set of directions, and I can end up with a geodesic, and I can go to Y. You see?
Yes.
Yes.
All right. So it's a very complicated picture, this actually. So I can go out in almost any direction, in a dense set of directions, and I will end up at Y. You see? Is the picture clear?
Yes. Yes.
Okay. Yeah. So this is what so there'll be infinitely many geodesics from X to Y. They will be labeled by the group gamma. Okay. The geodesics will be indexed by the group gamma. Because they're labeled by the points of the orbit of gamma, and the orbit is in one-to-one correspondence with gamma, right? So they will be labeled by points of the by the group gamma. Okay.
And these projections of the geodesics which we get below, they will form some dense subset here down there.
Yes, they'll form well, no. Wait. Well, at X, they'll be dense at X, right? They're the vectors at X will be dense. The vectors at X will be dense, but they may not be dense in the whole unit tangent bundle.
No, I'm not asking that. I'm saying that geodesics, which we get down here, okay, so their union, like, then.
Oh, their union, yes, the union will be dense in the surface, yes. Yeah, because the union is dense above, so the image will be dense below. That's clear. Yeah, that's clear. That's clear. The union is dense above, so the image will be dense below. Correct. That's right. That's right. Yeah. That's easy. Yeah. That's easy.
Sir, I have a question.
Yeah.
So, is it possible that these geodesics can self-intersect?
Oh, they have to. Yeah. Of course, they'll intersect. Of course. Oh, they have to. They have to. Yeah. They have to. Most of them will self-intersect. Yeah. They have to. Yeah. The geodesics in this surface, they'll be complicated. They'll go around many times like this, and then go around and maybe then come to Y. They'll be very complicated. Yeah. They have to self-intersect. Yeah. They have to. Yeah. Okay, so is this all right? Yeah.
Yes.
Anyway, just to give you an example of what happens for a hyperbolic surface. So
There is some sort of dichotomy in this sort of situations, right? Like there are like images of geodesics with sort of planes of space or something else. Like, I don't remember correctly, I guess, but there is some dichotomy of like how images will, I mean, of this geodesics will.
Well,
So what is the I didn't understand.
I also like don't remember correctly. I just okay. I mean to say like some sort of like these sort of images of geodesics, etc. means GGS surface or something like that. Again. So either it could form a well, I'll maybe look up and this was a part of that concept birthday last year, and they were talking about this. Okay, I'll just skip it.
yeah, well, look, see, I mean, if I look at geodesics in the hyperbolic surface, if I look at simple closed geodesics, so without self-intersections, then the possible limits of those are kind of well understood. Those are what are called geodesic laminations. Okay, those are called geodesic laminations. Yeah, let me think 1 second. Let me think, yeah.
Maybe you can draw some pictures.
Well, yeah, I mean, geodesic laminations are a bit hard to draw pictures of. They're quite complicated. But they're basically, it's like a foliation, except it's not a foliation of the whole surface. It's a foliation by geodesics of a closed subset, a closed nowhere dense subset of the surface. Yeah. So, I mean, geodesic laminations in the universal cover, they correspond to a family of non-intersecting geodesics, which is invariant under the group gamma. Okay. So, for example, it could be just one simple closed curve like this. So the lifts, because it's simple, the lifts will all be disjoint, you see. So maybe you have one lift like this, and then another like this, and like this, and then like this, and like this, and like this, and like this. So this is a, I mean, this is a geodesic lamination with just one simple closed curve. Okay. So the lifts will all be disjoint. And then, well, you can have a geodesic lamination where, let's say you take a geodesic, which, let's say in this picture, it goes, you add, say, a geodesic like this. So this is going to spiral in below, it's going to spiral towards, it's going to spiral around, you see, towards this closed geodesic from one side and from the other. So, and then you take the images of this above. So I can't draw the picture. It's too complicated, but you can do something like this. Yeah. So yeah, I mean, geodesic laminations, those are examples.
Actually, okay, finish.
Yeah, those are examples of limits of geodesics. I mean, yeah. So limits of simple closed geodesics. But I don't know if there's some dichotomy, what you're saying, I don't recall.
Yeah. I can actually tell you a statement. Maybe it's very different. I guess I was like mistaken, but I can tell you the exact statement which I was telling. Is that
yes.
If you take a, okay, it's like very different. Still, yes, it's a convex co-compact hyperbolic plane manifold of plane at least 2 with friction ends, then you look at the closure of horocycles, then they will be properly immersed submanifolds. So either they will be horocycle or properly immersed geodesic submanifolds after translation. So yeah, it's totally different. Sorry.
Right, right. So any horocycle is either closed or dense. That is right. For horocycles, that is true. Yes.
Right.
Any horocycle is
Yeah.
either closed or dense. Yeah, yeah. That's right. That's right. That yeah. So I mean that you can see in a punctured surface. So let's say torus with one puncture. Okay. So this puncture here, this cusp, this corresponds to a point on the boundary, infinity. Okay. And then the horocycles based at this point, these will be closed horocycles in the surface. Okay. But if I take a horocycle based at a point which is not in the orbit of infinity, okay, so infinity will have a dense orbit on the circle. But if I take a point which is not in the orbit of infinity, so say some psi which is not in gamma infinity, okay, if I take any of these horocycles, this horocycle will be dense. I mean, I can't draw it, but it'll be dense.
Yes.
And in fact, it will be dense not just in the manifold. If I look at the normal vectors to the horocycle, right? So these normal vectors, like which point like this, you see the normal vectors to the horocycle, yeah? The normal vectors will be dense in the unit tangent bundle. Okay? So that will be an orbit of what's called the horocyclic flow. So I mean, so see the tangent bundle of H2, yeah, SL2, PSL2R acts on this simply transitively.
Yes.
Okay, this action is simply transitive. So the unit tangent bundle is identified with the group PSL2R, the group of isometries, orientation preserving isometries of H2. Okay. And so here you have the geodesic flow acting on the unit tangent bundle. This corresponds to the action of the diagonal subgroup okay, that's A, your A group acting on PSL2R by translations. Okay.
Yes.
And the horocycle flow acting on the unit tangent bundle. I mean, the geodesic flow, you know the picture of what it looks like. The horocycle flow is this, that basically you take a tangent vector. So that defines for you a point at infinity. So then that defines for you a horocycle passing through this point. And the horocycle flow will move you a length t along the horocycle. So if this is V, and if the horocycle flow is say psi t, then this is psi t of V. Is this clear? This is the horocycle flow.
Yes.
All right. And the horocycle flow, it corresponds to the action of the parabolic subgroup 1T01. So that's your N group acting on G. PSL2R. Okay. So this is the horocycle flow. And then, so these flows, they commute with the gamma action on the right. And so you can look at the action on the quotient. Okay. So the theorem is that for n acting on T1 sigma, which is T1H2 mod gamma, which is G mod gamma. All right. All orbits are either closed or dense. When gamma is a finite volume, finite co-volume lattice, when gamma is a lattice. Okay. So all orbits are either closed or dense.
Yeah, this was the exact dichotomy. Thank you.
Yeah, this is for horocycles. So all orbits are just horocycles. So I mean, rather lifts of horocycles to the unit tangent bundle. Okay, this is not in the surface. This is in the unit tangent bundle of the surface. Okay, and so this is the.
And this is true
here, yeah, this is true for G mod gamma of finite volume. Okay, this is true for G mod gamma of finite. Yeah.
I mean, like if we here you're taking like G fixed and you're taking gamma to be some lattice, I guess, so that it's co-compact lattice, etc.
Utsav, if you want to ask more, should we just do another meeting for 5 minutes? Okay, so just one for 5 minutes. Okay, fine. Another 5 minutes then. Yeah. So let me stop this and start another.